This diagram illustrates the dominant scientific belief of the ancient world regarding how human beings see. It's called the extramission theory. Thinkers like Ptolemy and Euclid argued that our eyes actively shoot rays of light outward to strike and illuminate objects in our field of view. At the time, science was largely an exercise in abstract reasoning. If you wanted to understand nature, you didn't conduct experiments. You studied ancient texts, deferred to the authority of early Greek philosophers, and used logic to reconcile their claims with the world around you. In the city of Basra, around 965 CE, a scholar named Abu Ali al-Hasan ibn al-Hasan ibn al-Haytham began to pull away from this tradition. He stepped aside from the religious and political conflicts of his era to focus his attention on mathematics and the mechanics of the natural world. He began to argue for a different approach, that human senses are prone to error. To find the truth, he believed a researcher had to actively question what they gathered from ancient writings and verify claims through physical observation. This shifted the focus of inquiry from the library to the laboratory. By treating inherited knowledge as a hypothesis to be tested, rather than a fact to accept, he began to develop the methods that would define his life's work. Ibn al-Haytham translated physical space into algebraic equations, bridging observation with mathematical proofs to lay the groundwork for analytic geometry. Watch the model shift to human vision. He proved the intramission theory, demonstrating light travels in straight lines, bounces off objects, and funnels into eyes. To verify his math, he constructed physical apparatuses using flat, spherical, and convex mirrors, alongside lenses. He created confirmable experiments that other people could repeat to get the exact same results. This sequence of proposing a hypothesis, building a physical test, and backing it up with mathematical proof preceded European Renaissance scientists by 500 years. By treating the universe as a measurable equation that could be tested, he moved physics out of passive philosophy and into the realm of active, empirical investigation. Looking at this photograph of the Nile River, you get a sense of its geographic scale. And yet, Ibn al-Haytham claimed he could use his applied mathematics to build a dam and regulate the river's unpredictable, devastating floods. That claim caught the attention of the Fatimid Caliph in Cairo, al-Hakim. Al-Hakim possessed absolute political power and was known for wild, dangerous mood swings. He summoned the mathematician to Egypt to execute the dam project immediately. When Ibn al-Haytham finally stood on the banks of the river, he faced a reality check. Observing massive ancient Egyptian ruins like this stone pyramid, he realized his theoretical math could not solve this physical engineering challenge. If the builders of the past hadn't achieved it, neither could he. He had a serious problem. Caliph al-Hakim did not tolerate failure. To avoid execution, Ibn al-Haytham devised a desperate escape plan. He feigned madness, exploiting a legal loophole that prevented the punishment of the mentally ill. The caliph spared his life, but placed him under permanent house arrest. His life as a scholar was now shaped by a factor he couldn't calculate, the chaotic and unpredictable variable of absolute political power. For years, Ibn al-Haytham remained locked away. Stripped of his academic freedom, his students, and his public life, he sat isolated in a darkened room. This demonstrates the exact phenomenon he observed during his confinement. A beam of sunlight pierced a pinhole in his wall. On the opposite wall, it projected a perfect, moving, upside-down image of the outside world. This diagram traces the geometry of what he saw. Because light travels in straight lines, the rays crossing through the tiny aperture invert the image. He replicated this effect to build the world's first camera Obscura, providing physical proof for his mathematical theories of light. He spent the remainder of his confinement running these isolated experiments. He compiled his findings into a comprehensive work titled The Book of Optics, detailing the properties of light and the mechanics of the human eye. Political imprisonment had stripped him of his freedom, but it inadvertently provided him with a constant, dark laboratory environment. In this room, he had the conditions necessary to observe and record how light behaves when stripped of external variables. Following the death of Caliph al-Hakim, Ibn al-Haytham was finally released. As seen in this courtyard of the Al-Azhar Mosque, he spent his final decades in Cairo, living modestly, supporting himself by copying scientific manuscripts near this center of learning. His analytical work wasn't limited to physics. He applied his systematic approach to moral philosophy, authoring Tathib al-Akhlaq. He argued for the complete human being, advocating rigorous self-examination, control over impulses, and detachment from material wealth. Ibn al-Haytham died around 1040 CE. Centuries later, the Latin translation of his Book of Optics became a foundational text for future scientists, including Roger Bacon, Johannes Kepler, René Descartes, and Isaac Newton. By insisting on physical proof over personal prestige, Ibn al-Haytham provided a blueprint for scientific inquiry. His work demonstrated that the natural world could be understood not through passive faith in the ancients, but through rigorous questioning and repeatable observation.